students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to teach you impedance, line admittance and the microstrip line. In the last lectures we have studied about the impedance, how we calculate the impedance from the transmitting end and how we calculate the impedance from the receiving end. Now, the left out portion will be covered today in this lecture. So, the first topic is the impedance in terms of reflection coefficient or the standing wave ratio. All of you are already aware with the terms of reflection coefficient and the standing wave ratio. So, when somebody asks you when the reflection coefficient, the standing wave ratio comes into existence, the only answer that you should answer is that when there is a mismatch in the impedance of the load and the transmitting end, or we can say between the characteristic impedance and the load impedance, and between the generator impedance or the generator end and the load impedance. So, basically what we say, the reflection coefficient terms and the standing wave ratio arises when there is a mismatch in the impedance, and mismatch in the impedance means ki apart from there is a incident wave, and when there is a mismatch in the impedance, then there will be a reflected wave. And how much is the reflected wave is defined in the terms of reflection coefficient, that is reflected wave upon the incident wave, and the standing wave, the wave which is combines the incident wave and the reflected wave is called the standing wave, and the ratio, that is by the combination of the incident wave and the reflecting wave, there is a maximum and the minimum of either in the terms of voltage or in the terms of current or in the terms of electric field or magnetic field, we have get the values and then max upon the minimum. For example, when we express that in the terms of voltage, it will be V max upon V min, and already we know that reflection coefficient and the standing wave ratio are related to each other, and here are the term, that is this is our standing wave ratio and it is related to the reflection coefficient rho by this expression. Magnitude of the standing wave ratio should be equal to rho minus 1 upon rho plus 1. So, now back to our topic, that impedance, how the impedance is measured in the terms of reflection coefficient of the standing wave ratio. So, this is our impedance and this is our characteristic impedance, and this is a formula from where we get the expression of impedance in the terms of what? Standing wave ratio. Z is equal to Z naught 1 plus tau upon 1 minus tau, where Z naught is our characteristic impedance, and tau is equal to mod of tau, that is amplitude, into e to the power j phi. And when we want to express this impedance in the terms of reflection coefficient, then we have to replace this tau with this rho, and we note that this tau will accompany the e to the power j phi also. That is why when we replace the tau, it will combine tau e to the power j phi with it. So, when we want to replace the values, then what we get? 1 plus mod of tau e to the power j phi upon 1 minus mod of tau e to the power j phi. And now what we will do? We will replace this mod of tau with this expression. So, this will be Z naught 1 plus rho minus 1 upon rho plus 1 e to the power j phi divided by 1 minus then again mod of tau rho minus 1 upon rho plus 1 e to the power j phi. So, when you want to write it, you will have this expression. You are able to see it, rho plus 1 plus rho minus 1 e to the power j phi by rho plus 1 minus rho minus 1 e to the power j phi. So, what we are exactly getting? We are exactly getting this expression, and when we assume that our system is purely resistive, a lossless medium, then in that case Z naught is replaced by the R naught, that is a pure resistive medium. Now, the important terms of a transmission line is the characteristic impedance, which is used to define the characteristic of any transmission line. And already in the equation also we are familiar with the terms the Z naught, which is our characteristic impedance. So, if we want to determine the characteristic impedance of any transmission line, we have to follow the given step. The first step is to measure the sending end impedance with the receiving end short circuited. First of all, we will measure the sending end impedance with the receiving end short circuited. So, what we will get? We will get the impedance short circuit impedance, and what by substituting the expression we will receive this expression. And the next step, measure the sending end impedance with the receiving end open circuited, and in that case our impedance will be replaced by ZOC, that is open circuited, and when we put the values in the equations already derived in the last lecture about the impedance from the sending end, then we will get Z naught cot H gamma L, and already we are familiar that gamma is our propagation constant. So, now Z naught and Z naught, we want to calculate the Z naught. So, now multiply this equation with this one, what we are getting? ZSC, that is impedance short circuit impedance, ZOC open circuit impedance is equal to Z naught square, and when tan H gamma L is always the inverse of cot H gamma L. So, this two expression will get cancelled and we will have ZSC into ZOC is equal to Z naught square. So, Z naught is equal to under root ZSC ZOC. This is what we are getting. So, we have to remember these steps, that if we want to calculate the characteristic impedance, we have to follow this step, and after that gamma, which our propagation constant is equal to attenuation constant and the propagation constant, and this is equal to this one. Now, the normalized term basically plays a very important role in any of the expressions in the transmission line when we talking about the very large values and the different step size is very minimum also. In that case, the normalized term plays a very significant role. So, that is why we are calculating the normalized impedance of a transmission line also, and normalized impedance basically is given by very small z, and it is equal to capital Z upon Z naught. And in the last expression already we have seen that capital Z equal to Z naught into 1 plus tau upon 1 minus tau. So, capital Z upon Z naught will be equal to 1 plus tau and 1 minus tau, and this is equal to R plus minus Zx, where R is the real part and x is the imaginary part, pure resistive case and inductive and capacitive case. And now, the maximum normalized impedance is given by, of course, already we know that R naught is the case when we have a maximum impedance in the lossless condition. That is why the maximum normalized impedance that is expressed in the terms of small z max should be given by capital Z max upon R naught, and when we want to change the value of Z max, then it is equal to V max upon I min, and it is equal to 1 plus tau divided by 1 minus tau, which is basically equal to our reflection coefficient. And the minimum normalized impedance, small z min, capital Z min upon R naught, V min I max R naught, and this is equal to 1 minus tau by 1 plus tau, and this is equal to inverse of our reflection coefficient. And we know that for every interval of half wavelength along the line, Z max and Z min is repeated, and by how much distance it is repeated? By plus minus lambda by 2. So we can say that Z max at any point Z along the Z line where the wave is propagating, it is equal to Z max Z plus minus lambda by 2. So, the distance between the two maximum impedance, normalized maximum impedance actually is lambda by 2, and the distance between two normalized minimum impedance is also plus minus lambda by 2. And why this happens? Because already we know that V max and V min are separated by quarter wavelength, and Z max is equal to reciprocal of Z min for every lambda by 4 separation. Here we can see in this figure also that this is the V max and this is the V min. The distance between two adjacent V max is lambda by 2, and the distance between two adjacent V min is also lambda by 2, but the distance between V max and V min, adjacent V max and adjacent V min is lambda by 4. That is why we can write this way also, Z max plus minus this is equal to this one. Now comes the line admittance. Actually, there is not much more difference between the line admittance and the impedance. The significance is that when a transmission line is branched, it is better to solve the line equation for the line voltage, current, or the transmitted power in the terms of admittance rather than the impedance. So, to ease out the calculation, in the case of a branched transmission line, we use the concept of the line admittance. Otherwise, the impedance is enough for us. The characteristic impedance and admittance are defined in the terms of Y naught, Y 1 upon Z naught, and it is equal to G naught plus minus J beta. So, what we are saying that admittance and the impedance are always related to each other in the inverse order. We can say Y naught is equal to 1 upon Z naught, Y is equal to 1 upon Z. Similarly, our normalized admittance also small y, capital Y upon YZ, and of course, this will be the inverse, that is why it is equal to Z naught upon Z. And if we want to express this in the terms of the normalized impedance, then it is equal to 1 upon Z. So, basically admittance and impedance are related to each other in the inverse order. Where we say the admittance, when we want to write the admittance, it will be inverse of the impedance. Let us now see one numerical related to our impedance. What we are seeing here, we have a lossless line having characteristic impedance, that is Z naught equal to 50 ohm, and terminated in a load impedance of 75 ohm, ZL is equal to 75 ohm. The line is energized by a generator which has an output impedance of 50 ohm. This line is energized by a generator whose impedance is 50 ohm, and an open circuit voltage in RMS form is given as the 50 volt, and the line is assumed to be 2.25 wavelength. So, when we talk about the 2.25 wavelength, what does it mean? What does it mean? Basically, it is when we talk about 1 by 4 is equal to 2.54. That means, this will be equal to lambda by 4 wavelength. So, by taking this into consideration, let us solve this numerical. First, what we have to solve? We have to calculate the input impedance, and for that first of all we write the equation for the input impedance and what is values with us. We have the value of the characteristic impedance, that is R naught, or we can say Z naught, and the load impedance. So, we will have the formula of the impedance, input impedance, in the terms of what? Z naught and ZL, because these two terms are known to us. Already we have gone through the numbers of equations of the impedance in the last classes, from which we contain the input impedance also, load impedance also, characteristic impedance also, but what formula we have to choose for solving the equation depends upon what value is available with us. So, the value available with us is load impedance and the characteristic impedance. So, that is why we will follow this formula. And now, ZL is known to us, R naught is known to us. So, R naught, ZL, R naught. So, first of all we will calculate the beta d. Beta d 2 pi by lambda, and as I have told you that it will be equal to lambda by 4. That is why d, distance between the lambda by 4, and when we solve it, lambda lambda cancel, 2 here 2, this will give pi by 2. So, when we put this in this equation, what we will get? R naught ZL plus J R naught tan pi by 2, R naught plus J ZL tan pi by 2. So, this value will be equal to 0 because tan pi by 2 give 0 result. So, what values are available with us? This will be so, this is the value we are getting. Now, the second thing which we have to calculate is the magnitude of the instantaneous load voltage. So, for calculating the magnitude of the instantaneous load voltage, we have to go through this formula. This is the formula for calculating the instantaneous voltage at the load. So, V plus is known to us, that is 30, and we have to know the magnitude. So, we will ignore this expression 1 plus tau L. So, we have to calculate the tau L, and reflection coefficient in that case ZL minus Z naught, ZL plus Z naught, ZL is 75 and Z naught is our 50. So, by calculating we will have this value, on substituting we will get 36 volt. And the last questions, instantaneous power delivered to the load. So, this will be equal to V square upon R and load, that is why V square upon RL, V square 36 volt we are getting, so that is why we are squaring the 36 volt and RL. So, this is the value we are getting. So, in this way we are able to solve the numerical related to the impedance. Now, moving towards the strip line. So, strip line is basically comes into existence after 1965, because prior to 1965 all microwave utilized coaxial, waveguide or parallel strip line circuit. So, with the development of the monolithic integrated microwave integrated circuit, microstrip lines and coplanar strip lines have been used. So, the common type of strip lines are microstrip lines, coplanar strip lines, parallel strip lines, shielded strip lines, and numbers of other strip lines are also available, but these are the most common type. So, this is a picture of a microstrip line, which is basically consists of first a substrate having a particular permittivity, and this contains a ground plane, and in between on the top side we will basically create a strip line conductor having a particular width and having a particular thickness, and this dielectric substrate also have a thickness, and this thickness is always very less as compared to the frequency for which this is designed. So, Microwave integrated circuit with microstrip lines are commonly used with chips. The microstrip line is also called as the open strip line. Modes on a microstrip line are only quasi-transverse electromagnetic, that is quasi-TEM. Thus, the theory of TEM coupled lines applies only approximately because here exists a quasi-TEM mode. Radiation loss in microstrip lines plays a very big problem at discontinuities, at short circuit post, corners and so on. However, the use of thin high dielectric materials considerably reduces the radiation loss of the open circuit, open strip. So, what we are telling you, if you want to reduce the radiation loss, then we have to reduce the size of H and we have to take a substrate having a high permittivity. Now, characteristic impedance of a microstrip line. So, what are the important parameters which plays an important role? So, the figure, the characteristic impedance of a microstrip line is the function of the strip line width, strip line thickness, distance between the line and the ground plane and the homogeneous dielectric constant. We can see dielectric constant, distance between the line and the ground and the width of the strip line, and already we have known that H should be greater than D. Now, losses in the microstrip line. The attenuation constant of the dominant microstrip mode depends upon geometric factors, electrical properties of the substrate and the conductors, and on the frequency. So, the major type of losses which occurs here are the dielectric losses in the substrate and the ohmic skill losses in the strip, and losses are expressed per unit length in the terms of attenuation factor, that is our alpha. For a ordinary transmission theory, the power carried by the wave travelling in the positive z direction is given by half Vi. This is expression for that, V and I. We can say V plus Z naught e to the power, combining this one and this one, and expressing this whole expression with the P naught, we will have this expression. Now, attenuation constant expressed dP upon dz upon 2pz, which is dielectric constant and the conductor loss. Now comes the Q factor of a microstrip line. Many microwave integrated circuit require very high quality resonant circuit. The quality factor Q of a microstrip line is very high, but it is limited by the radiation loss of the substrate and with a low dielectric constant. For a uniform current distribution of a microstrip line, ohmic attenuation constant of a wide microstrip line is given by this expression, and the characteristic impedance of a wide microstrip line, you have to remember this formulas, because basically what comes in your university's examination, that is basically the microstrip line introductions only, and wavelength in the microstrip line is given by this expression, and it depends upon the frequency and the dielectric which is used. Dielectric plays a very important role. Since QC is related to the conductor attenuation, it is given by this quality factor due to conductor attenuation is given by this expression, and for a wide microstrip line, the expression basically changes and it is given by 39.5 and within bracket H upon RS and frequency in the gigahertz, and RS is basically given by, which is our screen impedance, pi f mu upon sigma. Finally, the quality factor for the wide microstrip line is given by QC is equal to 0.63 H under root sigma, frequency in the gigahertz. For a copper strip, attenuation is given by this alpha is equal to 5.8 into 10 to the power of 7, and then it changes into this, and the quality factor Q d, which is related to the dielectric attenuation constant, is given by this expression. So, basically what we are saying that the quality factor due to conductor and due to dielectric differs very much in the case of a microstrip line. So, if we want to have the complete high quality factor of a microstrip line, we have to take both into consideration. The condition where the permittivity does not affect the conductor quality factor and due to dielectric quality factor. So, thank you for attending today's class.